going to take a look at the periodic table. We're going to focus in on the idea of trends. Now, a trend is a general direction in which something is increasing or decreasing. So as we look at the periodic table, and typically we read it left to right, top to bottom, what we should be able to find are some characteristics of the elements that increase or decrease both as you go across the periodic table and as you go down the periodic table. Now, what's that good for? Well, in a little while, we're about to enter the world of chemical bonding. And by learning these trends of what the periodic table does as you go element to element is going to help you with predicting elements' behavior when it comes time for bonding. So let's go ahead and get started. The first trend that we're going to investigate on the periodic table is atomic radius, also known as atomic size. So how big is an atom? And keeping the idea of trends in mind, we could come to expect that with all those different elements that exist on the periodic table, it's likely that the atomic sizes are going to be different from one element to another. So checking out the picture down below, I asked the question, how does it appear that we measure atomic radius? Well, if we take a look at what we see here, we definitely see two atoms side by side in both the scenarios here on the left and the right. Now, the problem with measuring atomic radius, and if you remember your geometry at all, the radius is half the distance of the diameter, or the center of a circle to the outside. The problem with measuring that distance from here to here is that electron clouds are very fuzzy. And fuzzy borders don't allow us to make really accurate measurements. But one thing that we do know is true is that the nuclei of atoms are dense, hard cores that can be detected very easily. So what that means is that what we could do is we could measure half the distance from one nucleus to the other, which is represented by the letter D, the diameter. Take 1/2 of it, and that's going to give us atomic radius for an atom. So now that we know what atomic radius is, it's basically atomic size, how do we describe the trend in it on the periodic table? Remember what a trend was. I'll pop it up one more time. A trend is a general direction in which something is increasing or decreasing. So how does it work with the periodic table? Obviously, this is an outline here of the periodic table. We see an arrow up here that says atomic size decreases, and an arrow going down that says atomic size increases. So what does that mean? How can we put that together in a better statement? Well, how about something like this? As we move from left to right across the periodic table, atomic radius decreases. So here's the left, and that would basically mean that these atoms over here are going to be big, and these atoms over here are going to be small or smaller. As we move from top to bottom on the periodic table, atomic radius increases. So what we could say is that as we go down here, what we can expect is that these atoms are going to get bigger. And the same thing goes on this side over here. So they start small on the top, and as we go downward, these atoms are going to get bigger. So there's a trend pattern in both the left to right nature of the periodic table and top to bottom. So the next question I'll ask is this: why do you think it happens? Well, it's not that complicated, because if you think about our energy levels, which we said as you move down the left-hand column over here, we basically have energy levels 1 through 7. And as you move from left to right across these energy levels, what we find is there's a greater nuclear charge. Try to remember what's in the nucleus of an atom. So here's an atom over here, and here's what's outside the atom. Inside of the nucleus, we have protons and we have neutrons. And the protons are charged positively, and the neutrons don't have a charge. So as you move from left to right, the positive charge of the nucleus increases. And what that does, it means it has a greater pull on electrons that are outside in this area here, in the electron cloud. So what happens as you go from left to right is you pull in those electrons closer and closer. So by the time you get all the way here to group number 18, you have so many protons in the nucleus, they have the greatest amount of pull on the electrons around it, which is going to make them the smallest. So let's put that into a couple of decent sentences. As the positive charge of the nucleus increases, it pulls the electrons in tighter and more closely to the nucleus until you reach the end of a row. Each new row has another outside layer, so it gets bigger. So basically what that's saying is as I go from, say, row number 3 to row number 4, it's basically like me putting on another coat, a coat of electrons, which makes me a whole lot bigger than I was before. As I reach the end of row number 4 and I go this way, I'm now going to be in row number 5, energy level 5, and I put on another coat. So even though I'm getting smaller as I go from left to right, each new row I get to, I got to put on an additional coat full of electrons. But as you move from left to right, that coat is going to shrink down as the positive charge of your nucleus gets bigger. Here's a diagram labeled atomic radius, and PM is picometers, coded by ball size. So picometers is a very small thing. It's on the order of 10 to the negative 12th meters. So you know you're talking really tiny when we're looking at sizes of individual atoms. But notice the trends as we move down. As I go downward this way, notice that they're getting bigger, and in terms of general trend, as I move from left to right on the periodic table, I'm getting smaller. So by the time I reach all the way over here in group 18, I have the smallest possible atoms for each of the rows. We can also take a look at S block and P block. This here being S is group 1 and group 2A. And over here is P block with group 3A through 8A. And you can see the general trend as we go from left to right. This A with a little halo right there, that's called an angstrom. That just basically means 10 to the negative 10th meters. That's what they measured these in. And as we move down, again, we increase in size. And as we move to the right, we decrease in size. In an earlier lecture, we said that we'd learned 2 I words in chemistry. One was the word isotope, and the other one is coming today, which is the word ions. Now, all atoms of a given element are electrically neutral. If you remember, they should have the same number of protons as the number of electrons if they're an atom. Now, that's true except when the number of something changes. Now, if you're thinking neutrons, your brain is still stuck on isotope. It's not that. But instead, with ions, it's not the neutrons that change, but it's electron number that changes. Now, let's go ahead and give an example. Let's imagine that we're magnesium. We have the atomic number 12, and that means we have 12, of course that means protons, because proton number guarantees identity. An atom then, and not an ion of magnesium, therefore would also have 12 what? And I hope you're thinking electrons. If you're thinking electrons, you're on the right path. All right. If in an atom, if the number of electrons changes, it becomes one of these ions. So here is our second word, ions, and it has to do with electrons and not neutrons. All right. Ions can be charged atoms or groups of atoms. So sometimes we can have ions that are a whole bunch of atoms stuck together that carry a overall charge. And these ions can be charged either positive or negative depending on whether the atoms gain or lose electrons. Let's see how that works. Now, an atom that gains electrons is charged negative. Now, that may sound kind of weird to you. How can I gain something and become negative? Well, here's the thing. It depends on what you're gaining. So imagine you may have a neutral friend. They're neutral towards everything. But they start hanging around with the wrong crowd who's very negative, and that negativity starts rubbing off on them. Your neutral friend may become negative as well, because what they're gaining is the negativity that's rubbing off on them. So if you're gaining electrons, negative charges, overall, you can become negatively charged yourself. Now, on the other hand, an atom that loses electrons is charged positive. So I want you to think about what is being lost. You're losing negative charge. So imagine that friend who has become negative starts losing their negativity by hanging out with a good influence, such as you. And by losing their negativity, they're in fact becoming more positive. So by losing negative charge, you then become positive if you are an ion. Now, the last thing I want to draw your attention to is the spelling that I've starred down here. Somewhere along the line, people believe it's okay to spell when you lose something L-O-O-S-E. Okay? And that is a big fat no. Okay? We do not lose electrons. We lose electrons. L-O-S-E. Please make the note mentally and make everybody happy. Please take a look at this atom that we have sitting up here. This is what we call sodium. And sodium, as you can see, has a nucleus in the center, and that nucleus has 11 protons, and you can see it right here. It also has 11 electrons. You can count them if you like. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. You'll notice that it has a 0 overall charge because 11 protons and 11 electrons will cancel each other out. Now, let's just say that this sodium atom happens to lose this electron. For some reason, it shoots out of there. And what's left over is this core of the 2 plus the 8 around it of 10 electrons. So overall, we have 10 negative and we have 11 positive. If we were to total that up, we get 1 plus overall. So this one here is a positive charge. So we now have a sodium ion. A sodium ion is charged positive because it lost an electron, as we can see right here. If we look down below, we can look at the idea that goes with the element fluorine. Fluorine has the atomic number 9, and as you can see, the electrons around it, here's 2, 4, 6, 8, and 9, and there's an empty space where I guess there could be an electron there. And what happens is, let's say that this electron that shot off of sodium, it kept going and somehow it found that empty space and it jumped and filled in the missing spot. Well, if that was the case, what we now have is we still have 9 protons in the core, in the nucleus, and that guarantees it as fluorine, but now we've gained a 10th electron. We have 2, 4, 6, 8, and 10, which means we have 9 pluses and we have 10 minuses. And if you add those two up, we get a 1 minus. So this one here is a 1 minus ion, and we call this the fluoride ion. And it has a 1 minus charge because it gained an electron. So it became negative by gaining electron. It happened to pick up the sodium atom's electron that it lost. The next term we'll look at is ionic radius. So we know what atomic radius is, but now we're on ionic radius. So now we're talking about atoms that are charged. So what we can say is that ion size increases with the addition of electrons, and the ion becomes more negative as well. If we take a look at an example of the chlorine ion down below, here's the chlorine atom right here, but if it gains an electron, notice what it looks like now. It's bigger and it has a negative charge. We call negative ions anions. So this is the chloride anion. Ion size decreases with the loss of electrons. So if we look at our sodium atom down here, we'll say it lost an electron shot off and went to another element. What we're left with is a sodium ion called a cation. So this is what we call the sodium cation. When you lose electrons, remember you become positive. So now, not only do we see a decrease in size because we stripped off the outer electron that was causing this atom to be bigger in size, but we also became positive. So we have Na plus to represent the sodium cation. The last thing we can kind of throw in here is think of, again, a social situation. And think of people who are negative around you, okay? And think of a bully. If you're negative, you act bigger. So if they have a poor attitude and they're bullying people, they act like they're all big and tough. But if you're positive, you act smaller. You're more humble. So in this case here, your size is smaller. You don't need to be all big and loud and bullyish compared to the anion who gained negativity and now they're acting bigger than they actually should. Next trend, ionization energy. The ionization energy, also known as IE for short, is the energy required to remove an electron from an atom. So in other words, we're trying to take an electron away from an atom that has electrons around it. I want you to think of who. So for example, what elements on the periodic table wants to hold on to their electrons the most and why? So if we imagine the periodic table, we have already learned electron configuration. We know that we're trying to essentially fill up all the electrons with available orbitals as we move from left to right across the periodic table. So what we could say then is elements on the right side of the periodic table are really close to having their outermost orbitals filled. Elements on the left of the table are far from having their outermost or valence shell filled with electrons. So who's it going to be harder to take an electron from? An element that's almost all filled up, or one that's not even close? I want you to think about that for a second. That leads to a rule called the octet rule. The octet rule states that atoms will gain, lose, or share electrons in order to have a full 8 outer valence electrons. So if you remember S, the S orbital is filled with 2 electrons. We have S1 and S2. And the P block is going to be filled when it has 6. So if we add the 2 from S block and basically the 6 from P block, we have a total of 8. And that's the happy spot for all of the elements on the periodic table, to have 8 electrons in their outer shell, and that's what's called the octet rule. So how do we describe the trend in ionization energy? So again, we have the outline of the periodic table. We have a couple arrows going left to right and top to bottom. So what we can say is this. As we move from left to right across the periodic table, ionization energy increases. Remember, these elements over here on this side, they're very close to having their outermost orbitals filled up. So what that means is that they're going to be really hard to take their electrons from, and that's what ionization energy is. It's how hard is it to take the electrons from them and make them ions. But the ones over here on the left-hand side, these over here, they all have 1, and these have 2 in their outer shells. So if you ask one of these elements, hey, can I have your electron? They'd be like, yeah, you can have it. I don't even want it. Because if you think about it, if you're a group 1 element with 1 electron, your valence shell, if you lose one, that puts you back another row up in this position right here, which means you're happy. So if you wind up in group 18 in terms of your electrons, that makes you the happy column. So that's where the octet rule sits, is that everybody wants to be like these noble gases right here. That's a happy place to be on the periodic table. So it's really hard to take electrons away from the right-hand side and very easy to take them from the left-hand side. So as we move from left to right across the periodic table, ionization energy increases this way. And as we move from top to bottom on the periodic table, ionization energy decreases. So as you go down and those ions and atoms get bigger, it's going to be easier to strip electrons away. And we'll see why in just a minute. Let's put into words the why of ionization energy before we leave this slide. And it goes something like this. Elements on the right side of the periodic table are really close to having their outermost orbitals filled. Elements on the left side of the table are far from having their outermost valence shell filled. They would gladly give up their outer valence electrons. The reason why it's easier to take an electron from an ion that's very large is called the shielding effect. And it goes something like this. The additional shells of electrons on the outside of an atom shield the loss of inner electrons underneath the valence shell. So I want you to imagine that an electron is floating right here on this atom. It's going to be pretty easy to snatch it off. It's sitting right there on the outside. But then I want you to contrast that with an atom like this, cesium, where an electron's on the outside. Again, it's going to be very easy to grab it, but imagine we were trying to grab that electron from underneath all these shells. That would be like me putting $1 on a t-shirt and putting on 4 jackets and saying, can you reach my dollar? And it'd be very hard because I have 4 jackets preventing you to reach it. But if I taped the dollar to the outside of my jacket on my shoulder, I said, can you try to take my dollar? You'd snatch it right off. You'd be like, yeah, it's really easy. It's right there on your outside of your shoulder. So these inner core electrons are very difficult to get to, but these outer ones are very easy because it's very big and bulky and it's sitting way over here on the outside. So what's going to happen then is the shielding effect allows for easy electron capture from outer shells. And the bigger an atom is, for example, these are all group 1 here. And it goes from lithium, hydrogen's number one, but as you move down, lithium to sodium to potassium, rubidium, and cesium. Notice that they get bigger with additional shells. Well, remember the jacket analogy. As I put on more jackets and I have that dollar, that electron taped to my outside, it's really easy to snatch it. So as I get bigger, it's relatively easy to take my electron away from me. The next idea we'll mention is electron affinity. An affinity is a likeness for something. So if I like something a lot, I have an affinity for it. For example, I have an affinity for tacos because I like them. So electron affinity is going to scientifically be the energy change that occurs when an electron is acquired by a neutral atom. That's electron affinity. How does it work? Well, if you look down here, we have a neutral atom, and we'll call this one here the atom that's neutral. Atom, and I'll put neutral in parentheses. And let's imagine that it is going to gain an electron. If it gains an electron, it then will carry a negative charge. Remember, when you gain negative things, you become negative. And you're also going to release some energy when it gains that electron. Because most atoms, although being neutral, they still want more electrons. So when it gets that electron, imagine that it's breathing a sigh of relief, saying, okay, I got my electron because I was a group 17 halogen. I needed one more to be stable. And that exhalation, that is energy it's giving off because now it's down to a more stable state. So imagine the question, who gains electrons most readily? So halogens, group 16, group 15, they're really close to having their outer orbitals filled. And if they get those electrons, they're going to be happy because then they're going to be like the noble gases in group 18. And they're going to let off a sigh of relief. And that's the energy we're talking about. So in terms of trends for electron affinity, as you move from left to right across the periodic table, electron affinity increases. So all these guys over here, they want electrons very, very badly, want E's, because they're pretty close. Remember, if they get 6 in their outermost shell plus the 2 from S block, they're at that magical number of 8 in chemistry that fulfills the octet rule. As you move from top to bottom down the periodic table, electron affinity decreases. So the smaller that you are, the more badly you want those electrons. Remember the shielding effect. So the ones down here, they have so many layers of electrons that the positive charge of the nucleus is getting blocked by multiple layers, and they don't want them quite as badly as those little ones that are at the top. So here's a couple of good sentences you can write down in your notes that describes how electron affinity occurs in terms of the trend on the periodic table. Most of the stuff on the left-hand side of the periodic table and in the middle are metals, and most of the stuff on the right-hand side of the periodic table are nonmetals. And here we're going to contrast electron affinity of nonmetals versus metals. This is oxygen right here. It's a single atom of oxygen. And oxygen, being a group 16 elements, has 6 valence electrons. And of course it wants 8. It wants an additional 2. So right now it has 1, 2, 3, 4, 5, 6, and it's about to get its 7th, which gets it even closer to being stable with that magical number of 8. So when it receives this electron right here, what's going to happen is it's going to give off some of that nervous energy we were talking about. It's going to give that sigh of relief. I'm one step closer to being completely stable. So it's going to be what we call an exothermic reaction. It gives off energy as it gets more electrons. Now metals, on the other hand, such as potassium, like we see here, this one has 1 valence electron in its outer shell. And it could either gain 7 or it could lose this 1 to be stable. So I want you to think, what's easier, for this metal to gain 7 more or just lose this 1? And I hope you're thinking lose 1, because if it does, then you have 1, 2, 3, 4, 5, 6, 7, 8. And that makes this potassium atom a happy ion. Okay? So I want you to imagine what it will take to give it another electron. It already doesn't even want this one that it currently has. It wants to get rid of it. And you're trying to force another electron onto it, this yellow one. So what's going to happen to do that, to give it another electron, it's not going to breathe a sigh of relief. Instead, you're going to have to force this extra electron onto it with some energy. So you can see 49.8 kilojoules per mole absorbed. And this is what we call an endothermic reaction, a reaction that requires energy to be pushed into it to make it happen. The next trend we'll mention is electronegativity. Electronegativity is a measure of the attraction of an atom for the electrons in a chemical bond. So it's very similar on some of the concepts that we've learned earlier. So it kind of goes like this. Here's the atom, and it is trying to attract these electrons. These electrons are going towards it because it's holding out a magnet that's oppositely charged to these particular electrons here. So atom's ability to attract a bonding pair of electrons is called electronegativity. He wants to bond with those electrons. Now, in terms of numerical values, electronegativity can be found from 0.7 to 4.0. And if you're in my class, you have a periodic table that has in the bottom right-hand corner the numbers 0.7 to 4.0. Each element has its own numerical value. Now, the higher that number is, the higher the electronegativity of the atom, and the greater its attraction for bonding electrons. So if it has a very high number, that means that it wants electrons to participate in a bond with something else. So the trend goes like this. It increases as you move across a period from left to right, and it decreases as you move down a group. So if we take a look at this slide here, we have hot and cold colors for electronegativity. Who's the hottest? Well, it's fluorine. And if you were to look up fluorine, you'd find out that it has an electronegativity of 4.0. And then on the low end, this cold end down here, we'd have francium and cesium at 0.7. This is as low as it goes. So these are not looking for electrons to participate in bonding with other things. They're trying to get rid of the ones they already have. So as we go up and to the right, what we find is that there is an increase in electronegativity. So we can say that it decreases as we go down, and it increases as we go from left to right. Well, what about group 18? How come they're not all red? Well, remember, they all fulfill the octet rule, okay? What that means is they have full outer shell orbitals, and they don't want any more electrons. This is who everybody wants to be on the periodic table. So they're essentially going to have very, very low electronegativities, like 0.0. They don't even make it onto this scale with color because they're so stable the way they are. And another look at the electronegativity trend, notice that as you start on the bottom left and you move up towards the top right, that's where you see the greatest increases in electronegativity. Remember, you won't factor in this group here because they're all stable. The last thing I want to mention is that new types of periodic tables are constantly in the works. We're trying to figure out how to make a perfect all-in-one design where we don't have F block floating down somewhere below. Normally, you could put F block into the periodic table, but would make it super wide and it would not fit on a piece of normal paper. So here's someone's idea about how to make one using a spiral type of system. And if you notice, all the groups are still represented together, and that means that they all have similar valence electron counts, and that they probably react chemically in the same way. There's even some attempts to make it look like this one here. So this is a spiral type of formation that eventually might wind up in something like 3 dimensions like this. So we're constantly on the lookout for better ways to arrange and possibly look at the periodic table. All of these are works in progress, but they have to follow the rules where valence electrons should be the same, which dictates their chemical properties. So I hope you guys understand the trends of the periodic table a little bit better. It's a lot to take in one sitting, so rewatch if necessary. Make sure that you take good notes and that you're constantly drawing out the outlines of periodic tables and then putting arrows going to the right and going down and telling whether those trends are on the increase or the decrease. Now here's a tip for you. It's if you're asking the question, how am I going to know all these trends by heart? One of the trends goes in the opposite direction of the other 3. See if you can figure out which trend that is, and if you know the one that goes in the opposite way, you know all 4. Anyways, I'll talk to you guys next time. Hopefully you can figure that out. Keep reading that book and keep watching your lectures, and I'll see you later. Bye-bye.